This video is going to introduce you to the establishment of sizing procedures and to the definition of optimization issues which are related to it. This is the last lesson of this module. Until now, we've been able to discuss the establishment of scenarios and mission profiles, allowing to size different components according to the major design constraints of the system, simulation, evaluation and estimation models, allowing us to compute constraints of utilization and the principal characteristics of our components. We now have to use these informations in order to select the right components and at the same time optimizing our solutions regarding mass, dimensions, etc., respecting several constraints, speed, temperature of our working, and many more. Preliminary design is just like any other conception problem, an inverse problem. The objective is to select the right components for determined architecture. The models we use generally allow us to determine the inverse relation, which means the performance of our system, what's required in the specifications, based on components characteristics, what systems engineers look for. We essentially find two different kinds of solutions to this issue, either procedures of selections, sizing, which is a smart chain of calculus and tests, permitting to determine the components we must choose. These procedures can also be represented under graphic forms, directed graphs or digraphs, or n-square diagrams. The other solution is optimization algorithms, minimizing the difference between the performances we obtain and the performances that were required by modifying the design parameters of the components. We are going to introduce here how to represent in the form of graphs these two types of solutions. Causal diagrams represent the sequencing logic of calculus and computations thanks to graphic blocks. A calculus block receives physical quantities as an input and delivers the same kind of output, now able to be used by other calculus blocks. The linkage between different elements is not always easy to discern, notably under the aspect of algebraic loops. An algebraic loops, also called circular references in spreadsheets, correspond to a block that requires input variables depending on the output variables. We often meet this case during sizing phase when the choice of a component depends on its own characteristics. An n-square diagram is a causal diagram that possesses a well-established organization convention. Inputs are stored in columns, outputs are stored in rows, and blocks are arranged on the diagonal line in the order of computation. A DSM matrix represents a sizing problem in the form of a table, where design variables are stored both in rows and columns. Crosses indicate the variables which are necessary to compute another variable. The problem is well sequenced, which means without any algebraic loop, if the table is a low triangle. Crosses above the diagonal indicates the presence of algebraic loops that can be eliminated by reordering the sequence of computations. Here, the maximum simplification has been applied to the problem. A succession of calculus can also be represented thanks to graphs. Therefore, the equation 1 links in a non-causal way 4 variables. The links are not oriented, which means the output variable of the equation hasn't been chosen yet. After we determine the orientation of calculus, only one quantity can be generated per equation, as shown by the arrows in the example. When we dispose of several equations, we can represent all the variables and equations in the form of a bipartite graph, also translatable as a dependence matrix. So equations are ordered in rows, variables in columns. A right sequencing choice, which means the choice of the computed quantities and the position of the calculus, leads us once more to triangular representation of this matrix. Therefore, we'll use this type of representation to put our computations in order. It is not always possible to choose a component via a sizing procedure. It is therefore sometimes necessary to represent a part of the sizing procedure like an optimization issue. Here is its mathematical formulation. The objective is generally to minimize or maximize a certain objective, given by the function f, such as the total mass of a system. This objective depends on sizing variables gathered in the vector x that have to remain in a certain domain, such as a reduction ratio or a geometric positioning. The solutions must respect some equality or inequality constraints, such as remaining under a given temperature. This optimization problem can be represented in a graphic form, with the sizing variables as inputs, the rectangles, and the constraints and objectives as outputs, so the diamonds. Many optimization algorithms are available. An algorithm with gradient follows the strongest slope on the objective function. It quickly converges, but can suddenly stop on the local optimum and not on the global optimum, as both solutions are characterized by a null gradient. It is possible to start the optimization algorithm with several starting points, multi-start options under Excel, or to use slower algorithm but less sensitive to this kind of issue, such as genetic algorithm. The best kind of solution can also be obtained based on a constraint. It's actually very typical when it comes to solving engineering issues.